Well, thank you very much for, I think, for the organizing committee that invited me last year, and it's a real pleasure to do this. I've mostly refrained from giving online talks because they normally just don't feel quite the same, but here, where it's such a friendly group, it's actually quite nice. This is a materials science community by and large. So what I wanted to do is focus a little bit in what I have to tell you on how one can expand the materials horizon, at least in sort of in 3 different perspectives of how to do that. And just to give you a very quick glance at what it is that we do in my lab, we're sort of combining the intersection of electronic structure, physical structure, with ultrafast dynamics and transport measurements. And often these are questions of interface, that this is really where our interest has been for a long time and still is. So what you see here are nano junctions where we can look at transport through single molecules. This turns out to be very much an interfacial problem. We're working on both on different sorts of interfaces of thin materials. Now, the type of material that I want to concentrate on today is the 2D materials, broadly defined. And since this is presumably quite a broad audience, allow me to sort of give my own perspective of what I think is special and just to situate things here a little bit. When I say 2D materials, what I really mean is van der Waals layered materials, so materials that grow as a bulk crystal in a layered structure, and the layers are held together by van der Waals forces. Of course, the classic one that almost every school child now knows about is graphite, which when you exfoliate it, you get graphene, which is this monolayer of carbon atoms that are 1 atom high and many, many microns wide. And the result of this transition from a bulk material to this 2-dimensional situation is that you get strong quantum confinement, and it's that quantum confinement that really changes the properties. Graphene, of course, was given the Nobel Prize, and there's been lots and lots of new and interesting physics that has come out of that. A little while after the discovery of graphene, people started to realize that there are other such materials that fall into that same pattern where you have a van der Waals layer crystal. And so the next big wave that then came has concentrated on the transition metal dichalcogenides, or TMDs. I'll give you here 2 examples: molybdenum disulfide, tungsten diselenide. Much the same idea, only in this case, maybe your layer is 3 atoms high rather than only 1 atom high. And again, as you go from a bulk crystal to the monolayer or sometimes few layer, you see the emergence of new properties. I'll come to that in a minute. So it's this fact that you have layered materials that really makes them interesting. Now, there is a large number of 2-dimensional materials. You might call this the periodic table for making 2-dimensional materials. It's expanding, but this still captures the majority of the ones that you typically see. So you have these transition metals that are usually combined with a chalcogen of some sort. That's very common. You also have the Exciton classes. These are more like, for example, gallium or germanium sulfide. And all these materials grow layered or have at least a phase that is layered, that can therefore be thinned down to monolayer or near monolayer thicknesses. Sometimes you grow them through MBE or such processes, and new properties appear. There's some, I added a few additional ones here: chrome iodide, platinum selenide, and so on. And now also in the last few years, we've seen lots of ternary compounds coming along. So this set of materials is certainly increasing and goes much beyond the typical 3,5, 2,6 type semiconductor properties that you can get. Now, if that's not enough, then you can combine individual layers or few layers of one with another, and you can make these heterostructures. This can lead, for example, to an optical excitation that doesn't stay within a layer, but instead undergoes a charge transfer. The electron might hop from one layer to the other, and you get a charge transfer exciton. This thing has a much larger dipole moment that you can use. It also has different dynamics and different properties, so people do that. And you can then, of course, make this arbitrarily complicated, although the arbitrariness is limited by the patience of your students and postdocs. This is a very difficult thing to do well and reproducibly. But even then, in addition, you can not only just layer them, but you can also twist them with respect to each other. And that twist, again, leads to different electronic interactions and therefore different flavors of these stacked 2D materials. Now, as a result, these two-dimensional and layered materials really span pretty much every electronic phase that you might dream of. They come metallic, superconductive, semi-metallic, insulator, and so on, lots of semiconductors. And then along those and among those, you also get lots of correlated phases and often tightly packed together. So if you're interested in correlated materials, if you're interested in phase transitions, either dynamically or otherwise, this is an ideal playground to play in. Right? You have large selection and you have these very strong quantum effects that manifest much more readily. So I'll just give you a couple of highlights of the sorts of things that you can expect. One, for example, is that has received a lot of attention. I know at ASU people are working on this as well, is if you take two layers of the same material, for example, or at least two lattice matched materials, and you twist them slightly, then what's going to happen is you're going to get this Moiré pattern. Very classic, you see this here, and the Moiré pattern just essentially means that the slight twist and maybe displacement, lateral displacement, leads to the appearance of a superstructure, a modulation in your electronic structure, and that shows immediately. And this has all kinds of interesting and unusual effects. First of all, you can imagine that the potential energy landscape, if you do this with two semiconducting monolayers, for example, molybdenum sulfide, tungsten diselenide, that are almost lattice matched, that potential energy landscape gets modulated. And so that means you're going to get confinement in some areas where the potential is a little bit lower. If you now create a excitonic state that has a hole in one layer and an electron in the other layer, then you might be able to confine that, that exciton in the well. And since this is perfectly periodic, as long as your structure is crystalline, this means that you can generate a superlattice of excitons arranged periodically across the surface. And with low enough density, these form single quantum emitters and arrays thereof, which can be addressed. Typically, lattice spacing is 100 nanometers of the superlattice, 100 nanometers or less. Still, that is quite remarkable, and we certainly have tools to optically address such things. That'd be one example. Maybe the most famous example, which generated a huge hoopla, I think in 2018, from Pablo Herrera's group, was that if you take a bilayer of graphene and you twist it precisely by 1.1, I think, degrees it was, you get an unconventional superconductor that appears. Turns out he just demonstrated this year that in tri-layers, that's slightly different, but again, very low temperature, this can happen as well. This is not something that you would ever see in the monolayer, and it's definitely not something you would see in the bulk material. This comes strictly from this Moiré. And if you want to be a little bit flippant, you might say there were probably far more theoretical explanations for this than there were experimental demonstrations. So this is still an interesting and open question of what's going on. The transition metal dichalcogenides have unusual structure in that they have very distinct conduction band valleys and valence band valleys. And so you can create excitons in these valleys. And it turns out those excitons are actually locked to the spin. So a very specific spin can show up in a very specific valley. And so this allows you in these twisted heterostructures to generate spin-locked and sometimes layer-locked excitations. So quite unusual physics that you can extract from such things. Separately, or as a second set of examples, there is lots and lots of interest here in the direction of spintronics as well. And these are just some cherry-picked examples that I think are particularly exciting, but there are many more that are probably just as exciting. So there's been a demonstration, for example, of a spin tunnel FET, where they used a two-dimensional two-layer chrome iodide. This naturally is antiferromagnetic at the bilayer. But in the presence of an electric field, you can switch it from antiferromagnetic to a ferromagnetic state, and this can then act as a spin transistor. This again is a very powerful technology. It's a little unfortunate that chrome iodide is not very stable, but this certainly I think is groundbreaking. You can generate pure spin currents in graphene if you arrange your gates correctly. You can decorate your graphene and convert some of the sp2 hybridized edges and make them into sp3 hybridized. And in that case, suddenly the spin-orbit coupling increases by quite a lot, and this leads to colossal spin-Hall effect that you can measure. Again, this is for graphene. And then there's this whole business of not using the spin degree, but a pseudo spin. In the transition metal dichlorogenides, the plus K and minus K values are not identical. They're isoenergetic, but they're different. And this leads to a pseudo spin-like degree of freedom, which in fact, in the monolayer at least, which in fact, if you put this into a Hall structure, will separate the charges according to the value that they're in, whether they're at K or K prime, plus K or minus K, depending on where they are in the Brillouin zone. So very unusual. Again, this lends itself, of course, for quantum information applications and the like. Now, so my case is 2D materials or layered materials, which can be made low dimensional, are an extraordinary set of materials that's growing and that really give us access to new and interesting phenomena, new physics, which is sort of where my research group tends to be, as well as new applications and integrations, new material science. So what I want to do today, because of the fact that this is more materials end of things, is to show you 3 ways that we thought of, these are sort of 3 vignettes that we're thinking of how one can enhance the class of 2D materials or layered materials and make them 2D. And I'll do this in different ways, combinations with new different materials, as well as sort of changing perspective a little bit. So we'll be looking at expanding the family, as well as sort of different ways of thinking about when something is 2-dimensional or not so 2-dimensional. So in this first vignette, the first chapter, we're going to look at organic semiconductors. And those of you who know me from both ASU and U of A know this is an area that my lab has been active in for a long time. And that's always excited us. The organic semiconductors, for those of you who don't work in this, you should just think of them as being large pi conjugated molecules. So these are molecules with lots of p orbitals that are all in resonance with each other. And so within the molecule, you have delocalized of sorts electrons. And there's a huge, huge variety. Organic chemists can make gazillions of variants of these sorts of materials. And that is, I would say, in stark contrast to typical inorganic semiconductors, like where we have a handful. And even in comparison to the 2D materials, where we have an expanding set, this is still, there are, I forget what the current number is in the chemical abstracts, but it's something like 1 billion different compounds. Not all of them could be organic semiconductors, but just to say synthetic chemistry can really do just about anything you wish. And so what this is saying is you can then make, for example, semiconductors out of those, and you can pack them into devices. And people have made photovoltaics, light emitting diodes, thin film transistors, spin valves, you name it. And in all these cases, and this is now a slightly inflammatory statement, but I would argue that the interface between the organic semiconductor and whatever the other parts of your device is often absolutely essential and critical. In some cases, if your organic chemist has been good enough and has made a good champion material, it is the interface that will end up determining the functioning of the device. And so the interface, of course, is inherently something that's low dimensional. So this brings us back to the 2-dimensional aspect that I extolled earlier in the 2D materials. There might be an opportunity there. So my point here is expand the periodic table of semiconductors to include a group of materials that basically include carbon, nitrogen, oxygen, hydrogen, and maybe a few other things, a bit of sulfur, a bit of halogenides, and you're good to go. And you might then have inherently sort of 2D-ish like materials. And that then says that if I can take such organic semiconductors, I might be able to combine them with two-dimensional inorganic materials and generate new phenomena and new sorts of materials. And so I'll show you here an effort that got recently published in collaboration with John Scheibele and led by his graduate student Christine Monti at the U of A, where we took a TMD, so here I'm showing you WSE2, tungsten diselenide, and we combined it with a molecule. This is a fairly, PTCDA is a fairly common strong electron acceptor that people use in the organic semiconductor community. It's a flat disc-like molecule, and we basically made this structure. And we studied it optically, and in so doing, what we see here in blue, I'm showing you the photoluminescence spectrum. This is excited at 2.3 electron volts. And you see in blue is the sort of typical envelope that you would expect for a molecular photoluminescence of this molecule. And then in red is the heterostructure, the hybrid structure where you have a layer, a monolayer of this molecule PTCDA on WSE2. And what you see in there is some of the fingerprint of the WSE2, the so-called A exciton. This is your lowest exciton in WSE2, but also these very sharp transitions, which are Raman transitions, and those are Raman transitions of the molecule of PTCDA. So compare the monolayer PTCDA with the heterostructure monolayer PTCA and PTCDA on WSE2, and you see these enormous enhancement of the Raman transitions. We frankly did not expect that. So this was sort of it turned into detective story. Okay, so large Raman enhancement, which to us was unexpected. So we started to think about what's going on here. Well, the first thing that we thought about was, well, if you look at the band edge alignment of the WSE2 versus the PTCDA, you see that it should be quite easy, for example, to excite the WSE2 and then induce a charge transfer where the electron hops over to PTCDA, the hole stays in WSE2, you have this charge transfer exciton. Maybe this is what's happening. Well, if that's the case, then the extent to which you change the Fermi level in the chemical potential in this heterostructure should affect the extent to which you see these Raman peaks. And so we made a field effect transistor, a gated structure, really, and looked at what happens to these Raman transitions. And while you see here these X symbols, these are excitons of WSE2, you see that you have the neutral exciton, you can positively charge it, you can negatively charge it. So clearly we are quite substantially shifting the chemical potential. Absolutely nothing happens to the Raman lines. Right? They don't care about this. So this is not, the point is, this is not an effect that comes from charge transfer mixing, which in the Raman community and enhanced Raman community is often what people think of. So what might be happening? Our second thought was, well, let's just look at the photon energy dependence. And so when we did that, we saw that the enhancement, which sort of is somewhere between a factor, depending on the structure and so on, between a factor of 20 and 2, is very strongly photon energy dependent. And so we thought about, well, is this the case? Are we, maybe we're hybridizing the conduction band states with the PTCDA, but that turns out not to be the case. We see, for various reasons, we could exclude that. Instead, the conclusion that we reached is that we actually hybridize the excitons. So we're not hybridizing the electronic states, ground states, if you like, of the two independent materials, but instead we're generating excitations that form a new hybrid exciton. And Christine was able to develop a little model to do that. It's basically a two-level model, which she then plotted. And you see, even though we don't have the whole gamut of photon energies available because there's only some laser sources that we had, it follows quite nicely for all the different enhanced Raman transitions that we saw. So the upshot of this, and then if that's the case, you would expect that there should be a very strong layer dependence, which we could model. This is, again, in the case of WSE2. We showed it for other materials as well, MOSE2 and so And in each case, the behavior is very similar. There's slight variation in the absolute intensity of the Raman enhancement. But in each case, we see the strong layer dependence, and we see this, this clear Raman enhancement. So my point here is that if you use organic semiconductors, these can form new hybrid materials together with low-dimensional layered materials, which can quite significantly enhance the kinds of things that you can imagine doing. I showed you an example here of Exciton hybridization, so a new type of phenomenon that appears. But more generally, it's a much wider toolbox. And in fact, you can induce new phases. We have some work that's hopefully appearing soon, but that's a little too early to talk about, that really pushes this substantially. So I think there's a lot of scope here to play with for materials folks, as long as you're not afraid of molecules, which you shouldn't be. So the second vignette is focused on the fact that it can be difficult to grow these materials. And I will be the first to admit that this is not really quite the core of our expertise in my lab, but we're able to grow them. We have a CVD and MOCVD setup, so we can make them. That's how many people do it. You can, of course, a lot of work is done by exfoliation. You can stamp, you can MBE grow them, and so on. There's a variety of ways that people have made them, but it takes quite a lot of effort to do that and to make good, high quality materials. The more we work in this area, the more we recognize that there's a big difference between a 2D material and a good 2D material. It really matters in its optoelectronic properties and spin properties, what you do. And typically, when you do this, you get very high quality if you are diligent enough. But these things come then sort of micron sized, 10 microns, 50 microns, maybe for a single domain. You can make complete sheets, but they have many different domains. Now, for example, if you wanted to measure the band structure, that could be a problem. So how can you overcome this limitation? Our thought was, well, look, you take a three-dimensional material, the parent crystal, and you basically intercalate something. As long as you know how to intercalate things, then what that might do is it might actually generate a new phase that looks a lot more like a two-dimensional material. So this is what we set out to do. And then the immediate question after that comes, well, in that case, how do you know that things have gone sort of two-dimensional-ish? And so we very much like photoelectron spectroscopy. This is for us, a very powerful way to study the electronic structure, sometimes with element or chemical specificity. So there's a lot that one can do there to sort of track what's going on. So if you don't do this daily, here is just the cliff notes. You, of course, bring in light, and then you eject an electron. You might measure not just the energy of the electron, the kinetic energy, but also the angle, and that gives you the band structure. Now, in my lab, we can do this both in the valence band, as well as in the conduction band. They have slightly different names. One is called ultraviolet photoelectron spectroscopy. The other one is called two-photon photoemission spectroscopy. The details really don't matter. Suffice to say that usually photoelectron spectroscopy can look at the occupied levels, but with these two-photon photoemission types of experiments, and there's other types of now pump probe photoelectron spectroscopies, you can also access unoccupied levels or conduction bands. So that's part of the approach that we're going to use. So then let me show you what happens. So what we chose to do was to try and intercalate an alkaline atom. So we rain some potassium on there. And on the left-hand side is the ARPES, the angle resolved photoemission electron spectrum or band structure of the native MOS2. And then we add just a fraction of a small fraction of a monolayer of potassium. We have a lot of reason to know and believe that these things really intercalate. They don't just surface absorb. They intercalate by going towards step edges and then migrating into the three-dimensional structure. And what you would, of course, expect by adding something quite electron rich is that you dope it. And so you should see sort of an overall shift of the band structure to lower energies, because you've really moved your Fermi energy, right? You've added the chemical potential there. And that's indeed what happens. But what is quite striking is that this is not the same. This isn't the extent of this shift is not the same everywhere throughout the band structure. So at the gamma point versus the K point, we have about 150 millielectron volts difference. So this means that we're doing something quite different from just doping this material. We call this an electronic reconstruction. Note also that something interesting else happens, namely we start to populate the conduction band minimum. We pile enough electrons in there that we go and dope it to, if that's the right terminology, to such an extent that we have the conduction band minimum now filled with electrons. And in bulk, in the native MOS2, the band gap is actually indirect. And it is the conduction band minimum does not sit at the K point. By the time we dope it, it goes direct. That is one of the hallmarks that people use to know whether they have a monolayer of MOS2. And usually you check this with photoluminescence, PL spectroscopy, because suddenly going from an indirect to a direct band gap semiconductor, of course, you expect the luminescence intensity to go up dramatically, and that's precisely what happens. So very similar here. In fact, it starts to look like we're forming a two-dimensional electron gas. And I'll have some more evidence for that. The same is true in the unoccupied manifold. These are just some bands that I'm showing you here doing two-photon photoemission. The point is that there's a massive reconstruction here as well. So the intercalation really takes us from something that we understand well, that's a bulk three-dimensional crystal, to something that looks quite different when we intercalate it and starts to have the feeling of sort of two-dimensionalness. And so the remainder of this chapter here is trying to make the point that intercalation really changes you out of the bulk, some might say boring material, to something that is like a two-dimensional material, even though you didn't make true monolayer flakes of any sort. So what is happening here and how is that happening? That was the question that we then pursued. And what we're going to use is core level spectroscopy, and in particular, a sort of an unusual form of, if you like, time-resolved core level spectroscopy that can be quite insightful. And so to introduce that to you, because it's a very uncommon approach, there's only a handful of labs in the world that do that, let me sort of walk you through the principal ideas. So let's forget about core levels and let's just think about competitive kinetics. So imagine that I have a process that's relatively slow and I have some signature. And that signature only occurs if the process is relatively slow. Then I'm going to measure that signature. Right? So here's my little tortoise running along. If, on the other hand, I have same process, but now something is actually quite fast, then the signature will not appear. And so if I have a spectroscopic signature, then all I need to do is I need to measure the extent of that signature, and that should allow me to say something about the speed or the time scale with which this occurred. So to make this less cartoon-like, I'm going to go a couple of slides ahead here and just show you this competitive kinetics picture here, and then we'll go back and see how this is done. So consider a three-level system. And imagine that you have some process whereby we have a normal decay, which will be, for us, will be an Auger decay. That's our spectroscopic signature. We're going to look at Auger type processes. If a competitive process is quite slow, the Auger process will always win out, and you're going to see a lot of that Auger signature. If instead you have a competitive process that is as fast or faster than your Auger decay, then you will cease to see the Auger signature. Maybe you see something else, but primarily you're killing the Auger signature. So tortoise and hare again. Now, the kicker here is that Auger processes are extremely fast. Auger decays of core electrons occur somewhere between 0.1 and 10 femtoseconds typically for most elements. So what is it that we do? We take our material, we resonantly excite on a particular elemental edge. So for us, this is going to be the molybdenum M edge. So that's from the 3p to the 4d levels. And you're taking this basically atomic wave function, you project it up. And Normally, this thing would actually undergo Auger decay. And there's very characteristic Auger signatures, Auger peaks that you can measure for this decay. But of course, at the same time, this is not an eigenstate. This projection of this atomic wave function into, say, the conduction band is not an eigenstate of the extended crystal Hamiltonian. Instead, you should really think about this as some sort of wave packet. And this wave packet may undergo its own dynamics. And if those dynamics are fast and they spread out, then you will no longer see that Auger decay, or not as much. So we're going to look for the intensity of Auger signatures to give us a sense of the time scale of what's happening. And for the molybdenum M edge, the core hole decay time scale, the lifetime is 300 attoseconds. So that's very fast, right? So this gives us access to extraordinarily fast timescales that you don't easily have access to with regular pump probe spectroscopy. And it is not a pump probe spectroscopy. It's a single photon process that we induce that then, but it's also not a line width inversion or any of these other funky games that you don't want to play. It's using competitive kinetics. So let's play this out. Here is what an X-ray absorption spectrum looks like on the molybdenum M edge. You see that the M3 for the native MOS2, it turns on, gives you some very nice edge, near edge feature. And then we have two spin orbit components, so you get the M2 as well. Now, when we intercalate potassium into this, we see two things. First of all, we already know from the ARPES measurements that we do conduction band filling, so the intensity will drop, but it also shifts. What does that tell us? Well, here's the band structure of MOS2, bulk. And when we excite with the excitation energies and the polarizations that we use, we know that we're not exciting at the gamma point. This is not a momentum resolved spectroscopy in general, but selection rules still tell us that we're not exciting at the gamma point. Those are in the conduction band. Those are in-plane orbitals, which we don't have access to deliberately, but instead, we're actually accessing the M and the K point, which is where we saw the largest electronic reconstruction. These are out-of-plane orbitals, and the out-of-plane orbitals surely are the ones that we should be looking at if we're interested in what's happening with intercalation. And that's, after all, the orbitals that connect the different layers. So then, this is now a lot of spectroscopy geekdom. I will be brief here, but you spend a few happy days with 24-hour shifts collecting this kind of data. These are pretty hard experiments to do. And what you basically do is you change the photon energy and you measure some photoelectron spectrum to look for your Auger signature. You do this with potassium and without potassium, and you're going to compare. Now, what is the Auger signature that we're looking at? So we're going to bring in a resonant photon that takes a molybdenum 3p electron, it plops it up into the conduction band. Now you have this hole that's 300 electron volts down. That's obviously not the ground state of the system, so two things can happen. The electron can decay to fill the hole, and the excess energy gets released by ionization, that's the Auger process. Or alternatively, this conduction band electron can delocalize, somehow move off, and in that case, you're going to not see that same Auger electron. And so as we tune our photon energy across the molybdenum absorption edge, we see resonance enhancement. That's when we hit the conduction band. So this is where we need to be. This is just to show you what these kinds of data look like. Right? You're taking a lot of photoelectron spectra, you have to evaluate them. And ultimately what you're measuring is the resonant intensity as a function of photon energy. And you want to know the extent to which that resonant intensity changes with and without potassium intercalated. And down here, this is the main graph I'm going to draw your attention to. You see that there's a substantial change that is actually not dependent on which spin orbit component you're on. So what do you do with this? Well, if you know something about the clock with which in MOS2, these conduction band electrons decay through Auger processes, then by measuring just the intensity relative to the unadulterated MOS2, you can work out what the rates are with which an electron, after having been projected up from a localized atomic-like state into the conduction band, undergoes some dynamic change and disperses. And what you get from this is you see these vast enhancements here, but really the main thing is shown in the table. For native molybdenum disulfide, we know we can measure that the lifetime of such an electron is 1.24 femtoseconds. Okay, whatever that number is. This is much longer than the typical core hole lifetime of the molybdenum atom because it's in this molybdenum disulfide. But the moment we intercalate it, this time drops by a factor 3. So intercalation leads to a much faster decay of this electronically excited state in the conduction band. So this is now our element specific and, if you like, orbital specific fingerprint of what intercalation does. Let me interpret this for you. So what we're going to do is we're going from the layered MOS2 native to the intercalated system. And the first thing that happens is that when we put in these potassium, when we intercalate these potassium atoms, which kick off an electron into the bulk, they weaken, they lead to orbital rehybridization. We saw that in the X-ray absorption where we saw the shift and the change of the intensity. So we have fewer out-of-plane bonds in there. The second step that then follows is immediately that this means that the two layers, any two layers, but we usually only probe the top handful with this approach, start to decouple. And when they decouple, with all the electron density that we have in there, it's on the order of almost 10 to the 14 per square centimeter, we get large screening. This is something akin to a 2-DAG. And this screening changes the electron scattering rates, which then means that in fact, it increases them. And this leads to molybdenum electron delocalization. And that is the reason why the lifetime actually shortens. So this then is and this happens primarily at the M and K points, which are the points that we access. So to bring this all together here, what I'm telling you here is that intercalation as a general principle might be a good way to make large area, highly crystalline single domain materials with different properties. In our case, intercalation of alkali atoms, we show that this leads to a sort of quasi two-dimensional behavior that appears through layer decoupling, and we understand how that layer decoupling happens through the element selective spectroscopy, and that we can observe this on the native lifetimes of core excited states with orbital and element selectivity. So we're going to use this approach again for a different material to answer a slightly different question. And this is the question, do you even need monolayers? And lots of people would say, well, of course, because they have very unusual properties, time reversal symmetry or spatial symmetry might be broken. There's lots of things you can do there. But it turns out that's not really entirely true, right? You can grow, the typical transition metal dichalcogenide grows in the 2H phase. So this indicates the stacking of the different layers. But if you this is centrosymmetric, but if instead you grow it in the 3R phase, which is not trivial, but it can be done, then you are breaking this central symmetry, which is the symmetry that that leads to an indirect band gap. Instead, you actually get valleys, and you get the valley polarization. You get all these effects that I showed you earlier that happen in monolayers. Many of them, I shouldn't say all, but a number of them you can also observe in these 3R type structures. So here I'm showing you how in 2H, as soon as you go away from monolayer, valley polarization basically disappears, but it stays for 3R. This is seen in photoluminescence. So in other words, you can grow some of these materials with the kinds of crystal structures that allow some of the interesting physics that otherwise appears only in the single layer or bilayer or trilayer limit. Now, of course, you don't have to quantum confine them in the same way. That's something that you don't get. There's another way to say that you don't need monolayers. Alex Zunger showed this not so long ago, that of course, if you take inversion symmetric crystal, then overall, integrated overall momentum, spin polarization has to be 0 by conservation laws. But if this is a layered material, then within a single layer, there is no reason. A single layer may not be inversion symmetric. And so within a single layer, you may have indeed non-zero, a non-compensated spin polarization that only gets compensated by layering this material. And he showed this in some ternary material, but this would of course also apply to TMDs, to transition metal dichlorogenides, which in the layer, in the monolayer, are not inversion symmetric, but they become inversion symmetric in the 2H structure. That this is the case was very beautifully shown in a bunch of photoelectron spectroscopy experiments, where people took advantage of the fact that in photoelectron spectroscopy, you're only probing the top layer and maybe the second layer. And what you get then is interference of the photoemitted electrons in such a way that you get very strong spin polarization, right? And this can only happen if you are in fact looking at a single layer or two. So you're sort of looking at this local symmetry. And they showed this very nicely, that if you go from K to minus K, the spin polarization flips sign as it should when you go from plus K to minus K. So this is spin valley and layer locking. You can do this also with circular polarized light. And again, you see when you go left circularly polarized to right circularly polarized, the spin character changes from this to that. So, so the point here is that you don't necessarily need single layer materials for them to be truly two-dimensional. There might be different ways. What I skipped over here, and I will skip over, is just a statement that, in fact, some of these things have very unusual dynamics as well. So the value degree of freedom can live a long time when it doesn't live a long time, and the spin degree of freedom can live a long time. So we asked the question, well, how long or how soon is a material truly three-dimensional if we bring in the bulk crystal? Can we locally take advantage of the two-dimensionality, and therefore one would assume also of the unique properties of the two-dimensionalness, maybe in this case not by intercalation, but by looking at short timescales. Are these things two-dimensional and short timescales? And so what we said we would do is we would probe the electronic dynamics in cases where we're looking at in-plane versus out-of-plane electronic character. And again, this is something that we can do. This sort of orbital selectivity is something that we can do with core level spectroscopy, with element and chemical state selective electronic spectroscopy. The material that we chose is tin disulfide. It's again a layered van der Waals material. We have done a lot of work. I'm not going to tell you all about this, but we've measured the band structures. We've built some high efficiency, high quality field effect transistors. We've combined it with organic molecules and seen interesting effects there. So we had a good handle on this material, is my main point. So once again, we're going to do core electron spectroscopy. We're going to excite on the 3D edge. So this is now the M4 and M5 edge. And what you see here is the X-ray absorption spectrum. The main thing I want you to remember here is that there's sort of two regions. There's a shallow shelf region, which we'll call the A1 region. And that region contains mostly in-plane, is made up of mostly in-plane orbitals. And then we have the big sharp peak, which has out-of-plane character as well. And this is confirmed with band structure calculations that we have done as well. Again, we're going to do such a Auger map, or such a resonance photoemission map, where we change the photon energy and we measure the Auger character, the Auger signature, right? Rabbit and hare and tortoise. And you see that as we scan over the absorption edges, we get resonance enhancement, as we would expect, first on one spin orbit component, then on the other spin orbit component. So these are the core level transitions that one would look like. Now, here we're playing a slightly different game. What we know in here is that as we, prior to the absorption edge, we're going to have a regular so-called normal Auger effect, right? Just you clobber your material with a bunch of energy, you eject the core electron, and you're going to have an Auger decay. But once we get onto the resonance, then we're going to get an additional resonance component. And that component is a little bit different because it exists in the presence of a core excited electron in the conduction band. And so that means that we have a normal Auger component and what is in the community known as a spectator Auger. And they are much the same, but not quite the same kinetic energy because the core hole is screened in the case where you have an electron in the conduction band, whilst if it's the normal Auger effect, that's not the case. So if you combine the two of them, you get the overall envelope that we measure here. Of course, our problem is the opposite. We have to extract from this overall envelope the two components. Now, this can be done. I'm not going to bore you with how we did this. There's a bunch of spectroscopy that you have to work out. You can take this apart. And when you do that, then what I'm showing you here is in red, in the solid line, is this resonance component versus the normal Auger. And you see the normal Auger is more or less sort of constant as you would expect. It doesn't change that much with photon energy, but we get strong resonance enhancement when we run over the two absorption edges. Now, what is interesting is, recall that I told you that the X-ray absorption spectrum has a shelf and then a strong peak, a shelf and a strong peak. If we look at our decomposition, the shelf is here, no resonance enhancement seemingly, and then a strong peak. Shelf, strong peak. And then recall also that the intensity is our signature that we're going to use in this competitive kinetic scheme. When we see lots of the signature, we know things are slow relative to the core hole decay. When we see not much, we know things are fast. So we can take this apart. I'm overlaying the X-ray absorption spectrum, and I'm overlaying the calculated electronic lifetimes in the conduction band as we excite over the conduction band. And you see immediately that in this shelf region, we have very short lifetimes, fractions of a femtosecond, whilst once we hit the stronger absorption part in the higher lying conduction band, that lifetime shoots up quite a lot. How are we to understand that? Well, first of all, here's the difference. It's a factor 10 difference. In the shelf region, on the order of about 400 femtoseconds, attoseconds. In the main region, more like 4 femtoseconds. Factor 10 difference, same for both spin-orbit components, at least quantitatively. So how do we understand that? Well, here's the explanation. In the shelf region of the, so that's the lowest part of the conduction band, we are mostly in plane. We have mostly in plane orbitals. And so there, we would see therefore electronic delocalization in the plane. Whilst when we get to the stronger peaks, those contain a significant component out of plane orbital. These are the interactions between layers, and those are naturally slower. And this is maybe in some sense not surprising, right? The van der Waals interactions are weak, so layer to layer interaction is weak. You would expect the dynamics for charge transfer from one layer to another layer, or charge delocalization, I should say, to be slow compared to in plane. And that is what we're showing here with the core level spectroscopy. So in other words, this material, and this is pretty universal for the 2D materials, or layered materials, I should say, is that they, on fast timescales, even a bulk crystal is actually two-dimensional like. Again, you don't quite have the quantum confinement in the same way as you would have in a true monolayer structure, but you will harvest some of the effects that you get in a 2D structure already in 3D, but only at short time lifetimes, short time scales. So, in summary here, what I meant to tell you really was 3 things. We can think about layered materials and we can enhance the way that they use some of the aspects that come about when you go to low dimensionality by combining them with organic semiconductors. This generates new electronic phenomena. We can intercalate them, and intercalation leads to layer decoupling and maybe in addition to new types of behavior. And we can also go to short timescales. And on short timescales, they will be much more like two-dimensional materials. So I think it behooves us to sort of think about the bulk versions of all these interesting materials as not necessarily as boring, but as an opportunity to make them more 2D-like in various ways. Very briefly, I just want to advertise that there's new capabilities coming online in my lab. This is a micro RPS system, so this is going to be able to do band structure measurements on very short length scales, as well as chemical mapping on short length scales. This is how it was assembled in Germany. Then it got shipped, unfortunately, arrived in April last year, so it's been sitting in crates. But we had a first bout of installation in November, then COVID came back, so we're hoping to do the next bout of installation this coming week. This will give us complete 3D band structure mapping, and this will be also available to users. So if you're interested, if you have interesting materials, do contact us. You know how to find us. This is how we will be happy to collaborate with you. A few thanks in the work that I showed you. Several of my graduate students, Anubhav, Angel, Juyang, and Sarah, who are currently in the lab, and Callie, who just moved from BNL to MaxLab in Sweden, have done the bulk of the work. I've had the wonderful benefit of working with a superb set of collaborators. For this work in particular, I want to point out John Scheible and Brian Leroy, and then at SLAC, Dennis Nordlund, and at RME Labs, Mahesh Nupane, who have helped us with this work. And then here are the sources that have supported this work. Thank you very much for your attention, and I'd be happy to answer questions.
Thanks, Ollie. I think let's start off with the two questions that have been posted, and I'm sure there'll be more. Shantanu, do you want to?
Actually, I would prefer to let the other person ask the question first, then I'll ask at the end. Does that work?
No, that's okay, Shantanu. Jean-Luc, if you don't mind.
Sure. Fascinating talk, Ollie. Thank you so much. But the question I had was related to the hybrid organic semiconductor TMD excitons that you see in the Excited. I mean, you don't see anything happening in the ground state. So I was wondering whether, in a way, if we put it in terms of molecular terminology, it could be thought of as an exciplex.
So this, I've had hour-long conversations with people like Gary Rumbles to make the distinction between an exciplex, a contact pair, a charge transfer exciton. So in my mind, so actually maybe I should put this on you. What do you view as an exciplex? How do you define an exciplex?
Oh, I mean, that's the fact that in the ground state, there is no change in geometric structure or but then you get to the excited state and you have, well, that's an exciplex and not an excimer because you have two different materials or two different molecules, a donor and acceptor. And then in the excited state, you get some really strong geometry relaxation that can take place. And so I don't know whether that's something that occurs there, where, for instance, you would have a slightly different distance between your PTCDA and the surface that is present when you get that hybrid exciton.
Yeah, I think that's an interesting way to think about it, and one would probably, if we could somehow access the excited state physical structure of PTCDA, my guess from the Raman enhancement would be that indeed there is a structural relaxation up on electronic excitation and blending of the two excitons. So I would expect that might be a very fertile way to look at it. The thing that's always a bit puzzling, right, which I conveniently swept under the rug, is in two-dimensional materials, how do you actually generate that coupling? I mean, wave functions are extended. How do you get significant overlap between your inorganic wave functions and your organic wave functions. We do not think that this is defect mediated or anything like that. Right? So there's some unusual, the excitons are not completely delocalized, but they do have a much larger extent. Is that actually true? It might be on the order of the molecule. So yeah, so I think an exciplex view could be an interesting way to look at it and have some machinery available to probe this a bit more.
Okay. Okay. Thank you. Thank you, Oli.
I think the next question is from Samuel. Samuel, if you can unmute yourself.
Yeah, sure. Hi, Oliver.
Hey,
this is great. Hey, this is great. I have a question about the interpretation of your Auger spectroscopy from the second part of your talk. So it seems like you. This is actually a great slide right there. Yeah. So my question is, you totally renormalize the band structure when you do this intercalation. And so what I'm wondering is, what happens if the bottom of your band has more sulfur-like character instead of molybdenum-like character, and how can I differentiate between, bonding character, like elemental bonding character in my band structure, and that things aren't just going downhill to the sulfurs versus going into the potassium versus correlation effects? Or maybe I'm misinterpreting how you're interpreting your Auger spectra.
So let's skip through all of this stuff here. Yeah, maybe we stay here. So in some sense, you're exactly right. What we are seeing already in the X-ray absorption is the loss, the rehybridization and loss of in-plane flavor to out-of-plane flavor. Now, a downside of this core level spectroscopy is that you never see where stuff goes. You only see it disappear. That is the Achilles heel of this method. So unlike a plumb probe spectroscopy where I see disappearance and buildup, I never see the buildup here. And the experiment to answer your question precisely would be to repeat on the sulfur edge. Unfortunately, the sulfur edge, you don't really want to deal with sulfur 2p and 2s. Those are very weak transitions. You want to go to the sulfur k edge. And that is not accessible on that beamline. And on other beamlines, they don't have the instrumentation set up so that we can do the resonant photoemission. But that would be the appropriate experiment. So we looked at if we could do this overseas where we would have the appropriate beamline. I think that would really be a nice complement.
Yeah, sulfur is it's hard to get people to build photoelectron spectrometers at sulfur K for other reasons, but
yes, it is a miserable element to deal with in general.
Have you considered just doing the experiment on molybdenum diselenide?
Yes.
And then you have a selenium M edge. That's nice.
Well, you might think. However, in that same selenium M edge is a gazillion of Auger transitions, of high-lying Auger transitions of the transition metal. So we tried this, and it was so congested, we couldn't figure out a thing. It was miserable. So we gave up, and right now we're doing something on the tellurium edge. That actually works quite nicely. Different class of materials, right? Then you're looking at wild semi-metals and so on, but there's some very interesting questions there. But with tellurium, they're isolated again. But selenium, unfortunately,
you just crank up the spin orbit coupling all the way.
Yeah, exactly. Yeah. So there's some results there forthcoming that hopefully we're able to write up soon.
Thanks.
The next question is from Slava.
Hi, Oliver.
Hi, Slava.
I have a question, actually, the same slide that you used to reply to Jean-Luc about hybridization. So is this to enhance Raman scattering? Did you say that is hybridization between molecular exciton and the exciton on the inorganic side, or is with a charge transfer exciton?
It is not a charge transfer exciton. It is instead indeed it's in fact the hybridization of the B exciton, which is from the lower, so let me see here. The valence band in WSC2 is spin orbit split by about,
But then what?
700 MeV or something. It's very large.
But then what is the physical mechanism? Because I do not see how you would change the matrix element between molecular states for vibrational coupling if you do not mix an additional vibrational state, like in a charge transfer, you would add a cation or an ion. So what is the mechanism of enhancement in this case?
So the mechanism that we took here, and you know, we'd like to know more about it in all fairness, but the mechanism that we took here is some sort of excitonic coupling, right? Through so this would mean dipole-dipole type interactions, transition-dipole interactions.
Right, but you need to change the matrix element for electron vibrational coupling in order to enhance the Raman.
No, not necessarily. I think what's happening is that you get more resonance Raman scattering. So that's a key element, is that we're actually not looking at regular Raman scattering. We are very close to resonance Raman scattering, and that's what we turn on through mixing.
Right. So this I was mentioning resonance, because in resonance you have initial final state that goes in resonance.
That's
and
right.
You have a matrix element. Okay, we can talk about this.
Yeah. Maybe I'd like to hear more what your thoughts are there.
Thanks, Slava. Shantanu, are you still available to ask your question?
Yeah, sure. So my question is, I have actually two questions. One is causal and one is consequential. So the bilayer, the twisted 2D materials got my interest recently. So my question was, is the phonon dispersion expected to be different for the twisted bilayer graphene from the one for the Bernal stacked graphene?
I believe so. Yeah. And I think significantly, but the details I am not immediately certain of. But yes.
Okay, and the consequential question is, can we make a material, a 2D material, which is previously catalytically inactive, and by just twisting it at certain magic angle, can we make it catalytically active? For example, graphene, to say.
Did you say catalytically active?
Yeah.
So graphene probably wouldn't be your first choice, right? Because that's semi-metallic. You want to be in a semiconductor of some sort. So let's say we take a TND, again, we go to some magic angle, we generate we generate new phonon dispersion and different electronic states. So there is, I'm going to sort of answer by not answering your question. There is a lot of work where people do take these layered materials and use them as catalysts, including, following intercalation with lithium and things like that. I have mostly ignored that literature, so I'm not very knowledgeable in that literature. I know it exists. The mechanisms for the catalysis and whether the catalysis is enhanced in the few layer state versus, let alone in a magic angle, say, or special angle twisted state, I'm not sure if anyone has tried twisting and seeing if that changes catalysis. I'm sure,
exactly.
Right, so that would be quite interesting.
Ollie and Shantanu, I think there's some literature on that, because you're changing the electrostatic. I mean, basically you're changing the adsorption energetics in some sense. So you're creating different values for adsorption, and that could lead to some dissociative. I need to check the literature. As you said, I haven't looked at it, but I'm pretty sure that the dissociative versus associative adsorption energetics are probably dependent on the.
So we know that if you do it right, you can get as much as maybe 100 MeV modulation. And you're saying that might be actually sufficient to be catalytically relevant.
Yeah.
Okay.
That could be.
And and I also expect the magic angle should be different for every 2D material.
Oh,
Yeah.
very much so. And magic for what, right? So
Yeah,
the
like for
magic angle,
graphene, let's say it's
say-
1.1 degrees.
or in the bilayer, in the trilayer, I think it's 1.7 degrees to get to superconductivity.
Oh, okay.
So
And it's
there it can
material
change.
specific. Yeah, it's material specific too, right?
Yes. Oh,
Not
very
only
much
the
so.
layer specific.
Yeah. And I have not deeply followed this, but my sense is there isn't a really good understanding, a universally agreed understanding of why the magic angle is what it is, even in, say, the bilayer graphene structure, which people jumped on vigorously to try and understand what's going on.
But that's it's actually an interesting question, Ollie, because I mean, maybe Ankit could shed more light, but if I take a 1-1-1, layer, I mean 1-1-1 orientation of a metal and compare it with, it's supposedly if I can create the HCP variant, like the ABC versus AB, you think they may have different adsorption or catalytic properties like platinum or something?
I would bet my grandmother's pension on that. Which is easy. She's no longer alive, so she doesn't have a pension.
Yes, but that's a good question, Shantanu. That's something.
Yeah, thank you very much.
Are there any other questions? I think it's 12:10, so I think we're a few minutes over. But if any other questions, folks? I mean, it's been an extremely informative talk, and I should definitely add, Ollie, that it's a very refreshing change from the other talks, which were much more metal additive manufacturing and stuff.
If no, then I have a question. If
Shantanu.
So
very
actually,
quickly.
Yeah. So can we do the same thing, like twisting thing with the metals? Like if we deposit one monolayer of gold atoms and then stack another with some twisted at some angle on the top of it, and then you can see the electronic magnet and optical
sometimes properties. Most of the time, the forces for alloying are too high. The driving force for alloying is too high and you get an alloy. But for example, you can take a third of a monolayer of bismuth, and you can absorb that to silver, and you get a bismuth silver 2 top layer where the silver is rumpled a little bit and the bismuth sticks out just a wee bit, but it's integrated into the layer. So it's not quite sort of stacked and twisted, but you get a new top layer phase that is totally different from either bismuth or silver, and it's not really truly an alloy. So sometimes you can do that, but usually alloying is what gets you, at least with the coinage metals that I'm most familiar with. With the true transition metals, less sure about that. Those are much harder to process, right? They're often refractory and miserable to deal with experimentally.
And for the same metal, it may not be favorable, right? Like stacking.
Yeah, no, they're the metallic bonds or such that they're just going to conformally.
Shantanu, I think Ankit has a question, and then I can wrap up with one minor question.
Sure.
Ankit.
Thank you.
Thanks, Krishna. So Ollie, thanks for this really nice talk. My question is more from the engineering perspective. I'm an engineer, so I tend to look at things from a very engineering perspective. So just a very curiosity, it's a curiosity question rather than anything else. So what is the current status of studies on, you talked about the processing and the structures and things like that, but what is the status on the reliability of these organic semiconductor devices? Especially that they're like subjected to environmental stresses like irradiation or I guess electronic discharge. So then my other part of the question is, can we design these materials that are resistant to such stresses? Like, can we adapt these materials or the process?
There has been enormous progress. People will now often add encapsulation layers just to keep out oxygen and water, for example. And that's I would say almost routinely possible now. And that really helps. I think there is a fundamental challenge, at least for, well, no, let me first say something good. You know that at least in some instances, the status is such that it's industrial production. Right? You can buy AMOLED screens for TVs and cell phones and so on. So on the LED side, it's probably not a solved problem, but it's certainly a problem that is under remarkable control given how young this technology is. On the photovoltaic side, what is challenging is that usually for an optimal power conversion, what you do is you make these so-called blended bulk heterojunctions, where you take two flavors of organic semiconductors and you mix them together into a combined film and it has to be mixed just so. But that's not its thermodynamic equilibrium state. Right? With a bit of heat, it will undergo phase segregation and other complications. And of course, they are not 100% efficient. So even if they work well in the beginning, there is a degradation that comes from, I think, phase changes, if you like, and microstructure changes over time. UV photo damage, I think, can be a problem. I think that can be managed, though. Again, you can imagine I'm not sure if that's done. I would imagine people do that, but you can imagine putting filters on top that strip out the UV so that you don't get too much photo damage. I am not aware of commercially viable photovoltaics yet. There are various companies, fewer in the US than there used to be. There's still a handful in Germany. I think there's quite a few in China who are really pushing this. I think at the moment, mostly for niche applications, like window tintings and things like that. So it is still, for power conversion, it is still challenging to do. Thin film transistors and LEDs, it's working pretty well.
Okay.
And then the other part is, do you want solution processing or do you want to have vapor phase processing? Right? And the opinions separate there. A lot of people will say, well, it has to be solution processing, roll to roll. Some others might say, look, we do know how to do things by vapor deposition, and that at industrial scale that can work too.
Cool. I think we've hit the 12:15 mark, Ollie. So I think let's close the questions, and folks, feel free to email Ollie if it's okay with Oliver.
Absolutely, yeah.